In the past set of videos, we talked about the magnetic field and the force due to magnetism. We want to expand this idea of the magnetic field and magnetic field lines in this video. The concept of the magnetic field can be developed in much the same way that we developed the electric field. That is, we can think about finding a charge, particle, in this case moving, determine the force, and use the Lorentz force law to get us the value for B. So we say here that the magnetic field, by definition, its magnitude, is the maximum force on a charged particle, Q, at speed V. So if you have a charged particle going this way and you measure some force, let's say there was some V, and for that we measured some force for this Q. But then we found that if we sent the particle in a different direction, we measure a different F. At some direction, we would measure a maximum F. And that force would be perpendicular to the velocity direction and also perpendicular to what we're going to call the magnetic field. We'd take that value of the force, divide by Q, the charge on the particle, and the speed of the particle, and that would get you B. Remember, F was QVB sine of theta. So all we've done is find the direction in where that's equal to 1, and then unambiguously this becomes F max. So we measure that and divide by Q and V, and that gets us the value of B, our magnetic field. Now, we already have a way to find the direction of the magnetic field. We could use a compass, for instance, and put it through space and map the actual direction. So we have a magnitude now, and we have a direction. Notice how we did it for electric fields. For electric fields, we found that F was equal to Q times E. So we took the force and divided by Q. Here we're taking the force and dividing by QV. The other thing that's really important, again, even on these guys, the F and the E were aligned. The F and the B are not aligned in magnetic field. So there are some subtle differences that we're going to have to deal with in talking about magnetic fields. So at least that's the conceptual idea, that if you can find the force, just as you could find the electric force, you could have divided by the cause charge, you could have got E. So it was force over charge. Here, it's force divided by charge speed. It's a moving charge, a current that creates magnetism, and therefore a current that experiences magnetism. Now, the direction of the magnetic field, as I said, can be found by compass. It's important to remember that the magnetic field vector lies along the direction in which no force is measured due to its motion. This is exactly the opposite of the way the force of electricity is. In the electric force is in the direction for a positive charge that you would experience the force. So it shows you the direction of the force. The magnetic field vector lies in the direction of no force. That's very, very different. Now, we said we can build up a graphical picture of these magnetic field lines. There are some important differences and there are important similarities. So here's some similarities. The magnetic field lines will leave the North Pole. So if you have a North Pole of a magnet and a South Pole, North, South, the field lines leave the North Pole. And they enter on the South Pole. So they terminate on the South Pole like a negative charge for an electric field line, and they leave the North Pole like electric field lines leave positive charges. So in that sense, they're similar. Magnetic field lines never cross. If they crossed, that would mean that a compass would have to point in two directions at the same time, and that's not true. The magnetic field has a single numerical value and a single direction at every point in space. The density of the magnetic field is proportional to the strength of the magnetic field. So the density of the lines is directly related to B, in the same way that the density of the electric field lines is proportional to the strength of the electric field. Now, in order to map this, like I said, we could use a compass, but the easiest way to map field lines is to use something like iron filings. The iron filings act like little compasses, and when you shake down on them, they will actually align up. And you can see this in the following video. Here we're going to put some iron filings around a bar magnet in order to map the field lines. As the iron filings go down, you can see they're attracted to the magnet, showing the field lines coming out of the north side and circulating around to the south pole of the magnet. While there are many similarities between electric and magnetic fields, there are some very striking differences that one needs to understand. The graph of the magnetic field, when you're graphing field lines, doesn't completely specify the force on a charged particle in the way that it does for electric fields. In an electric field, when you look at electric field lines, you know the direction that a positive charge will experience a force at every point in space. In a magnetic field, you do not know from the field lines the direction of the force, or even if there will be a force, because it turns out that if the charge isn't moving, there's no force. If the charge is moving parallel to the lines, there is no force. So the direction of the force depends on the direction of the velocity as well as the field lines. And the magnitude depends on the velocity of the particle as well as the field line. So the force is not defined, not completely, just by knowing a graph of the magnetic field lines, and that's very different than electric fields. The magnetic field line doesn't point in the direction of the force applied. We talked about this previously. It points in the direction in which there's no force, so that's obviously different. Maybe the most startling thing about it is that the graphs for the magnetic field lines in static problems do not flow out in the way static electric field lines flow. Magnetic field lines, in all cases, static and non-static, that means for moving charges that move at constant velocity in a straight line and those that can change their amounts, their direction, so forth. The magnetic field lines for these will always circulate. They will never flow from a point, like for instance water from a faucet. So let me show you that. In electric field lines, you had, say, a plus charge. The lines flowed out. Now it turns out we can get them not to flow out. If we start moving this charge around, we can create waves in these things. We can cause these, by changing the magnetic field, we'll find out we could even make these electric field lines begin to circulate. But in statics, where charges are staying still, like we've covered so far this semester, these electric field lines all radiate out from a positive charge. That is not the way magnetism works. Magnetic field lines always circulate. They never flow. And this means it appears that there is no point source of magnetism. You can't just have a single pole. You always have a north and a south pole. And I'll give you an idea about why that is when we get to the video about current loops. So here's some things people could ask you. They could give you this field and ask you if this could be a magnetic field. Now, it turns out we could build things close to this by building what are called long solenoids. But eventually, no matter what, this field line, this B line, has to loop back. It has to circulate. It can't just flow like this. All right, so the S cannot be a graph of a magnetic field line. It may come way out here to turn around, but it's got to turn around. all of these lines have to turn around. Now let me give you some examples of magnetic field lines that we know about. There's the permanent bar magnet, and if we drew it, it would look something like this. It would have a field line that would circulate around, and it would have a field line that would circulate around like this, and it would have more lines that would circulate around, and it would have, say, another line that would circulate around here. Always leaving the North Pole, always entering the South Pole. You can also have a current loop. And if you want to find this current loop, you need to find the north and south. Put your fingers by the right hand rule, thumb wraps in I, and fingers point along B. And we'll show you this later. So if you wrap your thumb like that, and you wrap your fingers will curl up in here, so that's the north side, and they will ring around and come back in the south side. Like so. So you can see that the magnetic field of a current loop is very similar to the magnetic field of a permanent bar magnet. In fact, inside these bar magnets must be little current loops of some sort. And that was kind of bothered people because these are not usually good conducting materials, so what's actually making a loop? Turns out it's not macroscopic currents, it's microscopic atomic currents. We'll find out. And last but not least, the source of magnetic fields. The source of magnetic fields is currents. Moving charge. And the source of electric field is just charge. All right, talk to you on another video.